is somebody from abroad. Okay? Some people from Microsoft, company from Microsoft, Bill Gates gave them $1 million to come and give to us at our church. And then they have to come to Nigeria.
How's the time?
Country they are coming to.
Ah, good.
Then what will they now begin to ask? They will hear that, okay, inside Nigeria, that there are 36 states. So what will they now ask next? Which states? Is that we are coming to Nigeria. Inside Nigeria, which states? Inside Enugu state, where does Mass state? Is it Enugu?
You get used to it. That's why you're student.
You know, so
Tell
then
me
the
if something is
one
missing.
is local government, and then they will now go to his house. Is it not true? But inside his house also,
I will announce that one.
there could be another person that maybe there could be, you know, some of your cousins also have the same thing as you. Yes, I've seen two cousins who have such Chinedu and Chinedu. So in that case now, it can be Chinedu Okombo and Chinedu Okombo. So inside that family now, how do we now differentiate the two of them? We also find a way to differentiate the two of them to get the particular person we're looking for. Is it not true? That's what the quantum number looks like. So in simple terms, nobody will tell you to define what is quantum number. No. Just understand what quantum numbers are. Quantum number is just an address. Okay? So quantum number is just like an address of the electrons within the atom. Okay? Quantum number is just like an address. If you write it that way, anybody that sees your notes will know you know what you wrote. Okay? So the quantum number is just like what? An address to locate each electron within the atom. Okay? It's just like an address to locate each electron what? Within the atom. Okay? So the quantum number is just like an address to locate each of the electrons within an atom. Okay? Now there are 4 of them. So let's take them one after the other. So the first one, we have the principal quantum number. Okay, there are 4 of them. We have the principal quantum number. Then 2, we have the azimuthal quantum number. Then 3, we have the what? Magnetic. So we have the magnetic quantum number. And then we have again the spin quantum number. So we have the spin quantum number. So these are the 4 quantum numbers we know that we use to identify electrons within an atom. Okay? So no 2 atoms will have exactly the same 4 quantum numbers. Okay? We shall also see that. So each atom, each electron within an atom, can be identified using these possible quantum numbers. So we can use the principal quantum number to know the energy level of the electron. Is it on the first shell? Is it resident on the second shell? Is it resident on the third shell? Where? Within what energy level is it resident? Okay, so we shall take them one by one now. So let's get to the principal quantum number. So the first one will be the principal quantum number. Let's get to that one. Principal. So principal quantum number. Now we have this designation. This is represented as N. Okay, this is represented as N. Okay, and has values. This is represented as N and has values 1, 2, 3, 4, 5, and then continually, etc. Okay, this is represented as N. Okay, this is represented as N, and then has values 1, 2, 3, 4, and then moving on. Okay, has values 1, 2, 3, 4, and then moving on. Okay, so the principal quantum number has designation N, and then it has all of these. Now, it represents the volume. It represents the volume of electron cloud. It represents the volume of electron cloud. It represents the volume of electron cloud of electrons. Okay, it represents the volume of electron cloud. Okay, or the energy level of the electrons, within an atom. Okay, so at what energy level is this electron? Okay, so if we say, look at the shells now. So this is the first shell, N equal to 1. Okay, so we have the second shell n equal to 2. We have the third shell n equal to 3. And then moving on and on. So the shells, that is a designation. The principal quantum number is a designation of the levels, of the different levels, okay, where the electrons can be found. Is the electron on the first shell? Is it on the second shell? Is it on the third shell? So these shells, okay, have the designation of the principal quantum number. That n is the principal quantum number. Okay, so what is the number of the shell? Okay, in other words, what is the volume of electron cloud? Is the cloud of electron on shell 1, the cloud of electron on shell 2, and then that on and on. Okay, as simple as that. Then the azimuth of quantum number. The azimuth of quantum number. So the number 2 is the azimuth of quantum number. Now this has designation L. This has designation L. Okay, this has designation L. This has designation L. The azimuth of quantum number has designation L. The azimuth of quantum number has designation L and represents and has designation L, right? The azimuth of quantum number has designation L and represents the shape and represents the shape and represents the shape and represents the shape of the sub-levels and represents the shape of the sub-levels. Okay, represents the shape of the sub-levels or electron cloud. Represents the shape of the sub-levels. Okay, the sub-levels or electron cloud. Okay, now just listen carefully. Listen carefully. Now we observe that if you pass electrons, okay, if you pass an atom through a high-resolution magnetic field, okay, that there are levels, okay. The levels are split into sub-levels, okay. In other words, what we call orbital, okay. So the azimuth quantum number is simply representing the shape of each of these electron clouds, okay, that is built up by the formation of the electrons around the nucleus, okay. So the azimuth quantum number, if the value is L equal to 0, okay, is a designation that the orbital is what? Spherical. Do you remember this? Yes. Spherical. Okay? So L equal to 0 is a designation for spherical. And then we say that the orbital is what? The orbital is an s orbital. Okay? The level is an s sub-level. Okay? In other words, s orbital. Then if L is equal to the azimuth quantum number, okay, we have values we assign. If the azimuth quantum number is 1, okay, is equal to 1, then we can say that the shape of the orbital, so this is talking about shape, okay, the shape of the orbitals now, okay, these are the L values, so the L value, okay, the L value, and then the shape now, and then what orbital is it, okay, what orbital or sub-level is it, okay, so when L is equal to 0, then we say that the shape is what? Is a dumbbell, okay, is a dumbbell, and then the dumbbell is what? Is a d orbital. Okay, so we say that it is a d orbital that has the shape of a dumbbell. Okay, d orbital. Then when L is equal to 0, if L is equal to 2 now, rather, then we say that the shape is what? Double dumbbell. Very good. Double dumbbell. We say that the shape is double dumbbell. And then we will be talking about a d orbital. Is it not true? A d orbital. Okay? Then if L is equal to 3, do we know the shape? Me, I don't know, but you could know. Okay? The shape is complex. We don't know what to call it. Okay? So we don't call it any name. So we have the F orbital. Okay? We have the F orbital. That is an F orbital. Then for the shape of the orbital, an orbital is spherical or it is dumbbell. Okay? Dumbbell structure is that thing I showed you the other day. Okay? A dumbbell structure, like a double, an 8 like this. Okay, a dumbbell structure. So that is for the p orbital. So p orbitals have a single bell like this. Okay, a single dumbbell like this. Okay, this is a p orbital now. This is a p orbital. Okay, then if it is spherical, spherical orbitals are spherical. Okay, spherical orbitals are spherical like this. Okay, but double dumbbell orbitals, double dumbbell. Okay, double dumbbell, of course, has double lobes like this. Okay, there are double lobes. There are double lobes like this. So this is a d orbital now. This is double dumbbell. This structure is double dumbbell. Something like this is double dumbbell. That's double dumbbell. Okay, and of course you know s orbitals are you just have only one s orbital, right? S orbital is just only one, but p orbitals are three. Is it not true? Yeah. So s orbital is you just have s orbital, s. P orbitals you have px, right? Py, and then you have pz, right? Then d orbitals for d orbitals, okay, d orbital you have them 5 of them. There are 5 of them, right? Yes. So you have dxy. Can you name them? Dxz. You have dyz. You have dz squared. You have dx squared y squared. Okay. These are the 5 d orbitals. Okay. And then the same thing for f. F is 7, very complex. Okay. So as simple as that. So moving on now to the third one. We are trying to be fast so that we'll get to questions. The questions on this are very sweet, but they are also very funny at the same time. There are a lot of exam questions on this particular topic. Okay, it's very, very interesting. Now, for the next one will be what do you call it? Magnetic quantum numbers. Okay. So now let's move on to the next one. Magnetic quantum number. Magnetic quantum number. Now the magnetic quantum number is magnetic quantum number. The magnetic quantum number. You must know chemistry. You must know chemistry. Okay? The magnetic quantum number represents the orientation, the number of orientation. The magnetic quantum number represents the number of orientation. The magnetic quantum number represents the number of orientation. The number of orientation for each of the sublevels. For each of the sublevels designated by L. For each of the sublevels designated by L. The magnetic quantum number represents the number of orientations. The number of orientations for each of the sublevels designated by L. Now, this is related to the L. The magnetic quantum number is related to the L, that is the absolute quantum number, by deviation. M is equal to L plus 1. Okay? M is equal to L plus 1. And the values of M are given as plus or minus L. And the values of M are given as plus or minus L. The relationship, what did I even say about this? What did I say? Someone should read out what I said. It is related, the magnetic quantum number M is related to L by deviation. M is equal to L plus 1. And what did I say on this one? And the value of M is given as plus or minus L. Okay? The value of M is given as plus or minus L. Okay? Plus or minus L. Let's see what that means now. Let's see what that means. So now we have, let's see what that means. Now what that means is that for each of the L value, the M is dependent on the L value. The M value is dependent upon what the L value is. So for each of the orbitals now, okay, for each of the orbitals. So if for example we have S orbital, okay, S orbital, then we have P orbital, we have P orbital, we have F orbital. Okay? Now what is their M designation?
Master, talk on outside.
This is what?
Performance ataka Kenan.
D designation is what? 1. Then D is what? 2. And then F is what? 3, right? Now, for each of these now, what will their MO value be? Their MO value orbital is S. There's just only one orbital. This is S orbital. It's not true. There's only one value. There's one orientation. Now look at this now. Look at what this thing simply means. It simply means that if you come into any of the shell, that there are subshells. Is it not true? And inside the subshells now, there are other divisions of the subshells. For example, the S subshell, there's just one division of the S subshell. Then inside the B subshell, look at the B subshell now. The B subshell has 1, okay, and the value of L. What will be the value of L for it now? Plus or minus 1. And according to what we are told, plus or minus 1, M plus or minus 1, okay, plus or minus L simply means minus L, 0, and then plus L. Goes from negative to positive. Let's apply that to this now. So plus 1 simply means what? Simply means minus 1, 0, and then what? Plus 1. That is why P orbital will always have 3 numbers of orientation. There are 3 orientations. There are 3 values. There are 3 levels inside P. Does it make sense to you now? Yeah. There are 3 sub-levels, subdivision, orientations inside P. And that is why we often say that P orbitals are 3. Those 3 P orbitals correspond to what we have here now. So this is BX, this is that PY, this is that PZ we are talking about. Okay? Then what about D equal to 2? D being 2 now, D being 2, what do we have here? So D being 2 simply mean what? Simply mean plus or minus 2, right? And plus or minus 2 is what? Minus 2, minus 1, 0, plus 1, and then plus 2. So how many levels do we have here? The degeneracy, we call it degeneracy. Thank you very much, Holy Spirit. Degeneracy. Degeneracy, there are 5 degeneracies in D. Okay? So that is why we have those 5 orbitals. So those 5 orbitals in D, that's what we have here. That is what this value represents. Okay? And if you use that equation that we just introduced now, M is equal to L plus 1, you also see that it is going to give you all the number of values we have here. So M is equals to M plus 1. Simply means that when M is 0, what will happen? 2 times 0 is what? 0 plus 1 will give you what? 1 value. Then when M is equal to 1, what does it mean? 2 times 1 is 2 plus 1, 3. So that means there will be 3 values. When N is equal to 2, what does it mean? 2 times 2, right? Plus 1, 5. That means there are 5 values. You see that now? That's what that equation is telling you. That envelope is related to envelope by equation.
Should be your seat.
So for every value of envelope that is substituted,
Go to your seat. Go. Tell the person to
that are
come.
possible for that particular level.
Just put it.
So, what did I say for what? N equals to L plus 1. Remember this was the equation, we mentioned this equation before as the equation that relates L to M. Okay?